Hi, I'm Brian St. Pierre. I'm the Regional Business Development Manager for Rockwell Automation. At this point in time, you should have already heard how the power grid works, and you should be comfortable with why it is that the most common effect that we all feel in manufacturing from the power grid is voltage sags. Today, what I'm going to do is walk you through a presentation of just what those sags do, and I'm going to use some data from a power quality report here from the Milwaukee area. This report was taken from 3 different monitors on 3 different feeds, so we have a good snapshot of power for the past year here in Milwaukee. As we go through it, we're actually going to duplicate these events. This particular one that happened on February 26th, for instance. To accomplish this demonstration, we're going to use some very special equipment. I have with me a sag generator. This actually allows me to dial in the voltage and how low it goes, and for what length of time we sag the equipment. We're going to sag the equipment over here on my right, which is our control panel equipment. Typical contacts, relays, power supplies, encoders, and of course a PLC. In between, I've got a scope that actually allows us to see what the sag generator is creating and what the load is actually seeing with the events. As I generate these voltage sags, I want you to take a look at the monitor that displays the waveform, and we'll see the effect of that sag. And then on the right, the control cabinet itself, any contacts or counters or anything that drops off is actually going to turn on a red light. So we'll trap the fact that it's dropped out and come back on momentarily. So the first one we're going to do occurred on August the 2nd, and it dropped to 71% and lasted for about 20 milliseconds. I've set the system up to that, and I'm going to create that sag now. And we see on the monitor the fact that the generator and the load are seeing the exact same event. It's only just over a cycle long, and of course we've dropped out this relay. This is probably the most common relay today on emergency stop circuits in most factories. Of course, if that relay drops out, the line's going to stop. And people are going to wonder, how did that happen? How can they get it going? And unlikely that they'll actually attribute that to any kind of a voltage sag event. Let's try another one. On August 13th, at about 9:03 a.m., we dropped to 65% remaining, and it lasted for 30 milliseconds. So I'm going to set that up on my system right now. And I'm going to generate that sag after I clear and we'll see the effect of this. So now what we find is not only have we dropped out the same relay, but we've also lost the contact. Again, depending on the equipment that you have engaged, this could have an effect on your entire line or a particular machine. And again, we see it's just over about 2 cycles long, or not quite 2 cycles long, at 30 milliseconds in length. On September the 18th, we had another event occur, and in this case it dropped to 55% remaining, so it was a little deeper sag. We'll go down to 55% with our depth, and in this case it lasted for 160 milliseconds, which is just a bit over 1/10 of a second. And again, I'm going to clear the load, and we'll see the effect as I push the sag generator button. So now you can see the sag in this case is much longer, and what we've done over here on a control side is not only have we lost that contact and relay, but the encoder as well. If you had a robot on the line, you just dropped the bits that tell it what position it is in, and of course that means that you're going to have to rehome the robot. If you got a conveyor with an encoder online, the bottle you thought you were going to kick off isn't going to be the one you're going to kick off. And of course your PLC program, since it's running, is likely going to stop the line and say, wait, reorient, get things back in sync. Okay? So let's do another one. On February 26th of this year, at about 9 a.m., we had a voltage sag in the Milwaukee area that dropped to 37% remaining, and it lasted about 70 milliseconds. So I've set my system up for that. We're going to generate that sag and see the effect. Here we've lost the contact, the relay, the counter, as well as the DC power supply. What you might notice here is that the PLC is still running. Typically, the PLC is the most rugged component in the entire cabinet. It's everything that's hooked to it that's at risk of dropping out from this type of a sag. Again, would the lights have blinked? I'm not sure. It's only about 4 cycles long. So it's probably, that won't be attributed to a power sag. We'll do one more and call it good. On May 28th, we saw a sag that dropped to 18% remaining and lasted for 60 milliseconds. So I'm going to set it up for 18% remaining. About 22 volts. Reset my load center and create that event. Now we finally dropped everything offline, including the PLC. So in this case, what we would know is this has occurred on one phase. Anything hooked to that phase in that facility is just gone down. I think this demonstration gives you a pretty good idea of what can happen to the manufacturing processes when voltage sags occur. Things will drop offline, sometimes mysteriously, and people are going to spend their time trying to fix problems that maybe aren't real, things that aren't broken, and so on. So what about when things really do break, right? Well, voltage sags have a very detrimental impact on power supplies. And of course, power supplies are just about in everything, including drives. And the reason they have that detrimental effect is because all power supplies have a circuit in it like this one. This is a diode rectifier circuit, and it's a fairly simple concept here. You simply flip the switch on the left side of the screen here, and you start to charge the capacitors on the right side. Okay? When you reach about 80% of full charge, that power supply has what's known as a soft charge circuit involved, and that's going to bypass itself so that you have actually access to power when the power supply is working. So it needs to have free access, and you don't need anything slowing it down. When a voltage sag occurs, the electrons that were sitting over there on that capacitor have just gone to ground. And so now the capacitor wants to be fed. And at the end of the voltage sag, what we have is a current inrush that comes in to feed the capacitors. Unfortunately, the bypass is closed around the soft charge circuit. That means there's nothing in place to control that surge that takes place. It looks like this. On the left side, we see normal inrush, and you can see the amps being well managed there as they come in to charge our power supply. On the right side, what we see is a voltage sag, and you can see in the top part of this where one phase is actually sagged down, and then the sag ends just here, and at that point in time we see a spike that occurs, and that spike is actually 5 times as great as the current inrush that takes place at startup. This is going to stress the components in that power supply, and if it turns out that that power supply was engaged at the moment in time that sag happened, it's probably going to burn it right up. And the damage will look like you had a spike or a hit by lightning, because the front end of that power supply is going to be fried. What people won't recognize, it probably was the squirrel down the street that died that caused that voltage sag that just took out that drive or that power supply. So now that we have a better understanding of what voltage sags can do to us in our manufacturing environment, what do we do about it? Well, in the end, you keep power a constant. And if you look at this example, what we see is there's really 3 ways to keep power a constant all the way down to 0 volt sags. First one would be a UPS. If we run off the batteries, then whatever happens up front is not going to affect us. Secondly, you might use a flywheel. Here we're actually going to generate our own power. So spin a weight, and what happens up front to that energy spin in the weight isn't going to matter, because the weight's going to continue to spin for a period of time. The third choice is a dynamic sag corrector, or DySC. The DySC is a different kind of device. It's a series device instead of a parallel device. It actually turns on, corrects the problem or mitigates the issue, and then turns back off when the problem's been corrected. In 99% of the time, it's simply in a monitoring mode. So here we show that the power flows from the utility through a static switch in our DySC system to the load. And it simply monitors, waiting for that sag to happen. When a voltage sag does happen, it turns on in less than 2 milliseconds. On average, 1/10 of a cycle. Once it's on, it now becomes the power supply. So the flow of power now goes from the utility through our power matrix, our double conversion power core, and back to the load. We have a double conversion power core, so we're actually going from AC to DC and back to AC again, and recreating exactly the sine wave that had been present prior to the voltage sag. For the most part, we do this by stealing current, and that's what the power matrix allows us to do. So if I lost phase 1 entirely, I'll simply double the current on phase 2 and prop that voltage up using that extra energy. And I can play this game stealing current to prop up voltage for up to 5 seconds, and that is the limitation of the DySC. So that wraps us right back around to the question of what's your problem? If your problems are all under 5 seconds, then the DySC might be the right solution for you. So now we're back to our demonstration, and what I'm going to do is put in series with the load a dynamic sag corrector, or DySC. This is one of our mini DySC systems. This particular unit is a 2 amp system because we have a very small load here. I'm going to utilize the same settings we did for the very last sag we created, which you can see here on your monitor, that took down our entire system. Resetting the system so we have our program going again, and then once again recreating the sag. And if you look at the monitor, you'll actually see that waveform reappear on the top of the screen, showing the sag generator created that sag, but if you notice on the bottom of the screen, the load never saw it. The DySC came on, turned on, and recreated the sine wave during that period of time. Let's go ahead and create a couple others here. I'm going to change to 70 milliseconds and go back to one of our earlier events. Again, I don't have to reset anything, but just to again show a difference. Once again, I'm going to switch this up. We had an event that lasted 0.160 or 160 milliseconds long. In that case, it was at right around 50%. So we'll go up there and recreate that event. And once again, you can see the sine wave has been regenerated. The load is not seeing any difference from these voltage sags. Thanks so much for your attention during this demonstration. As I get ready to hand it back to your local teams, I just want to point out that the DySC systems that we have here are available from 1 amp to 2400 amps and pretty much everything in between. So if you're having issues, there is a solution. Thanks.